So let us see about excess pressure case. The three cases we see. Whenever a liquid drop is formed or a soap bubble, there is a more pressure inside compared to outside, atmospheric air. Excess pressure inside a soap bubble is given by 4T by R. In case of soap bubble, inside is also air, outside is also air, totally doubles the pressure acting on it. The same excess pressure inside a liquid drop is equal to 2T by R, where R is the radius of the bubble or liquid drop, T is the surface tension of the excess pressure inside an air bubble in a liquid. If an air bubble is formed inside a liquid, the excess pressure that experiencing by the air bubble in it is equal to 2T by R. Again, R is the radius of the air bubble and T is the surface tension of the liquid. These are the three important relations to be known to understand the pressure or radius or surface tension. They give interrelation questions on the basis of these. And laterally come to angle of contact. Let's come to the angle of contact concept. Whenever we take a liquid drop on any surface, which may be wet the surface or does not wet the surface, why happens so is the nature of cohesive force and adhesive forces. Cohesive force of the liquid drop is stronger than adhesive force between the liquid drop and the solid surface. Then it does not wet. If the cohesive forces are weaker compared to that of the adhesive forces, then adhesive force becomes stronger and wet the surface. That's the basic reason. So how the angle of contact is defined is, draw the tangent to the liquid surface, and this tangent makes some angle with respect to the solid surface within the liquid. Where it wet the surface, we observe like this, and which does not wet the surface, we see that the angle is more than 90 octaves. It's a liquid drop and a surface. And if that is just the angle of contact mean, on what factors depends? Temperature increases, angle of contact also increases. As temperature of the liquid increases, angle of contact increases. Impurities, soluble impurities, are added to a liquid. Then angle of contact. So this is reverse as for the other earlier. Surface tension is observed. In case of surface tension, increase of temperature decreases the surface tension. Here increases the angle of contact. But addition of impurities to any liquid, surface tension decreases. Here also angle of contact also decreases. There are two cases, and along with capillarity, I consider the comparative statement for angle of contact and capillary rise and meniscus nature. Coming to the capillarity. Capillary means long tube having radius very negligible compared to its length. The meaning of capillaries. When this capillary is taken into a liquid or dipped vertically into a liquid, there is a difference of pressure experiences inside and outside the pressure. In that case, there is a rise or fall in the level of liquid. Again depends on nature of this capillary tube material and the liquid you taken. If it wets the surface, then there is a rise in the capillary. or if it does not wet the surface, there is a fall in the capillary level. Rise or fall in the fall of liquid. Fall of liquid in the capillary is called that property as a capillarity. The property that we see, there is a rise or fall of liquid in the capillary tube, is named as a capillarity. So the question is here the two types. Liquid that wet the surface. We see the three things. If it wet the surface, angle of contact is less than 90 degree. Acute angle. Again, capillary rise. There is a rise in the capillary tube. Liquid rises in the capillary and meniscus happens to be concave. Concave meniscus. Suppose liquid does not wet. Does not wet the surface. Again we see the three. Angle of contact is more than 90 degree. There is a capillary fall. And meniscus become convex. That there is a dip in the level and level happens to be like this. Fall in the liquid level take place if it does not wet the surface. The most likely in this area the questions are coming. Capillarity means rise or fall in the liquid level when capillary tube is taken vertically into a liquid. When it rises or falls, when the meniscus is concave or convex, when the angle of contact is acute or obtuse, clearly by this. If it wet the surface, any liquid wet the solid surface, angle of contact is less than 90. But you know, in case of pure water and pure glass, it is almost 0. For ordinary water and glass, it is less than 90. For pure glass, water and pure silver, it happens to be equal to 90 degree. For mercury and glass, it is obtuse, about 138. So capillary rise take place in case of the wetting the surface and meniscus is concave. Whereas the liquid does not wet the surface, angle of contact is obtuse, that we take in the case of mercury and glass. Capillary fall, the liquid level falls in the capillary compared to the outside level and meniscus become convex. In this, we come to the expression for surface tension due to capillary rise. One of the experiment you maybe did in the practical classes. When we taken capillary tube into a water or any liquid, so there is a pressure difference and due to surface tension, liquid rises in the capillary tube and have a concave meniscus. It will rise up to certain height. The rise is due to surface tension. If angle of contact is theta at every point, this become vertical component. If it is t, this vertical component become t cos theta. So why the liquid rises up to that height only? The reason is weight of the liquid column must balance the upward force, because if you see here, total weight of the liquid column, if I call it as mg, total weight of the liquid column above the liquid surface, and there is a total force due to surface tension acting upward, which rises the liquid, which is pulling the liquid upward. At the same time, the weight of the liquid is pulling the column down. When they become equal, that will be in equilibrium position. Taking that force equal to mg, if you consider, Force is nothing but surface tension into circumference. T cos theta is a surface tension which is acting vertically upward. Its component taken along the vertical direction. And other is circumference. If r is the radius, is 2 pi r. Here weight, if you take r is the radius, it pi r square is area into height gives you the volume, density into g. So that gives you a relation. If you forgotten, you can take this and arrive at the expression for surface tension. So T is equal to pi cancels half rho g h r cos theta. For pure water and glass, theta neglected, and we take a relation half rho g h r. In case of water and glass pure, where theta is assumed to be 0, cos 0 become 1. But here there is a small meniscus correction also considered in some cases. We taken the height to the lower point. This column height h dash is taken as r by 3. And more appropriate equation may be written half rho g r into h plus r by 3 is the expression for surface tension. For a given liquid at a given temperature, T is constant. If you observe here, density is same, G constant, T same, H R product remains same, means in case of capillary rise, H is inversely with R. Larger the radius of the capillary tube, smaller is the height to which the liquid rises or falls. Applications are concerned, every liquid drop is spherical in shape. Because of this, cohesive force symmetrically acts from all directions radially inward. When you throw any liquid into this space, it will get a spherical shape, the number 1. And number 2, that because of the surface tension, the surface energy, a thin elastic membrane-like structure appearing on the surface, the light mosquitoes can walk or insects can walk on the surface of liquid, or mosquitoes' eggs are standing or floating on the surface of the liquid on stagnant water. The breeding of the mosquitoes, that's possible. So again we see in case of capillary action the rise and fall. Water rises in the capillary, particularly case of the sap rising to different parts of the plants through the fibers which are acting like a capillary. Or the blotting paper sucks the water or ink is due to capillary action. So this is what we have taken the surface tension, the second unit. So started with molecular forces, like each molecule have tendency of attracting the nearby molecule. That what we call it as a force of cohesion if the two molecules are of similar type. Example we taken as a welding. Whereas the two dissimilar molecules have a force of attraction between them, then we call it as a force of adhesion or adhesive force. Dissimilar molecules coming in contact with each other. But this cohesive force or adhesive force both are attractive, only dissimilar nature or similar nature. And this is leading to the concept of surface tension, because every molecule is attracting the nearby molecule. When you consider the surface molecules, they are experiencing two types of forces. One, cohesive force of the molecules which are below up to the surface, half sphere. Another half sphere above the surface of the liquid, you are seeing the adhesive force, that force between the molecules of liquid and that of the air molecules. And cohesive forces are stronger than adhesive forces, no doubt, because the density of liquid is high. And again, when you take the resolving components of these cohesive forces onto the surface, a tangential force appears. This tangential force per unit length, you defined it as a surface tension. Or other way, I can say that a molecule to come to the surface of a liquid, work is done against gravity. It's standing at the surface of a liquid. This is possible when a drop is coming up against gravity from the water. This work done is stored as energy in the molecule at the surface. That is called as a potential energy of the molecules or surface energy of the surface molecules. This surface energy per molecule, per area, surface energy per area, or surface energy per change in area, we define it as the surface tension, or surface energy can alternately define it as surface tension into area of the surface. But here we taken the very important part, that most important towards NEET is the work done or energy stored. Work done in forming a bubble, work done in forming a soap bubble or a liquid drop, or blowing a soap bubble or a liquid drop, or breaking a liquid drop into smaller drops. What the energy that releases or absorbs, energy absorbs during the breaking of the bigger drop into smaller one, what the changes in temperature comes, and what factors that change in temperature depends. Their surface tension, radius of the bubbles, and again Joule's constant, and specific heat of liquid, and also the density of the liquid. Again, small liquid drops can be fused into a bigger one. Again, work is done. The relation we come across. While we forming a bigger drop from smaller drop, the decrease in surface area, there is a release of energy take place. In breaking, there is an absorption of energy. But when you fusing them, there is a release of energy take place. Relations are similar, but only is smaller, big drop when become into smaller drops, total area of all small drops becomes bigger, more than that of a bigger drop. Therefore, we get, there is increase in area, that means absorption of energy and cooling of the surrounding. At the same time, when smaller drops are fused into bigger one, area decreases, therefore heat releases. That becomes the surrounding hotter. This is most important, along with relations, whether it is making a bubble or breaking a bubble. We want to know the relations perfectly to answer. And coming to the other part, we appear to the excess pressure. Excess pressure inside a liquid drop and also inside a soap bubble, or it may be in case of a air bubble inside any liquid. We have the relation for this. And later on we come to the concept of surface tension. This surface tension, again force per unit length, the tangential force acting on the surface per unit length on the surface of the liquid, we define it as a surface tension. In that, if any substance is lying on the surface of a liquid, if you want to take it out of the liquid, some force is necessary. What that force depends on surface tension into total length of that body. So it may be a wire, it may be a square frame or a square lamina or a rectangular lamina or any other shape, we have a relation. You have to think that what is the surface tension of a liquid, and secondly, what is the total length, maybe hollow or solid, you have to see, and total length of the substance, product of those two gives you the force necessary to pull it out of it. And even in case of, apart from that, we come to the concept of angle of contact. The angle made by a tangent drawn to the surface of a liquid, within the liquid with the solid surface, may wet or may not wet. If it wet the surface, angle of contact is less than 90 degree. If it does not wet, angle of contact is more than 90 degree. And again, capillary action is again due to, it is one of the concept of the surface tension application. That capillary, already we come to know what it is. Whenever vertically we take a capillary into a liquid, there is a rise or fall take place. This property of rise or fall of liquid, when a capillary taken vertically into a liquid is called as a capillarity. So how much rises and all this we take in the later equation. However, this capillary rise possible only when the capillary tube material, substance and liquid, so the liquid wet the capillary tube material and meniscus become concave. That's what we say. If the surface is wet by the liquid, angle of contact is less than 90 and the capillary rise is visible and meniscus inside the capillary appears to be concave. If it does not wet, then there is a fall in the liquid level, angle of contact is more than 90 degree, obtuse angle, and meniscus is convex. And finally, expression for surface tension we have seen, and height to which the liquid rises also we come across. And there is a chance that, suppose if we have a U-tube like different radii, of one may be R1, other may be R2, R1 and R2. And you are seeing there is a difference in the liquid levels. The difference of height is h. So what that height can be estimated? You know the relation that surface tension equal to half rho g h r. If you want h, you can take 2t by rho g into 1 by r1 minus 1 by r. The height level difference in the two limbs of the U tube may be helping you to measure t, or if you know t, what the height it can come to, where r1 and r2 are the radii of the limbs of the U tube. And even when one drop is pressing with the another drop, if may be of radius r1, it may be of radius r2, then when pressing each other, so in soap bubbles we see such situations, a bigger curvature will be formed of radius r. So this radius r of the curvature, interface curvature, can be shown to be equal to r1 r2 by r1 plus r. The relation we can show it. Or if two bubbles are joined to form a single bubble or drop, if it is of r1 r2 and if it is r comes, r is equal to root of r1 square plus r2 square. Two drops are fused to form a single drop. The radius of the single drop is equal to square root of r1 square plus r2 square, where r1 and r2 are the radii of the smaller drops. This is the summary of the second unit in fluid statics about surface tension. Very careful about what is liquid pressure and the surface tension concern the surface energy work done in different cases. Surface tension, excess pressure relation, surface tension relation, and maybe of these small relations on which the questions appeared in all the years in NEET or AAPMT.